I teach general chemistry, analytical chemistry, which is making chemical measurements, and environmental chemistry. And so sometimes people have this sense of, oh, I don't want any chemicals in my food or chemicals in my water, but to me everything is chemicals. And there's a lot of beauty in that, and understanding and unraveling at the molecular or atomic level how these things transform and in some cases, unfortunately, can negatively impact our lives. And so a lot of what I focus on in my own research and in my teaching has to do with water quality. And so I titled this talk, Water, Water Everywhere, Nor Any Drop to Drink. That may sound familiar to you if you ever read The Rime of the Ancient Mariner, talking about being sort of stranded in the middle of the ocean without any water to drink. And here we are, we're seeing huge effects of Hurricane Florence on our neighbors just slightly to the north of us within South Carolina and then up in North Carolina. And so sort of one of the ironies of these events is that they involve a huge amount of water, but oftentimes that water it comes through with such quantities that it can ultimately become contaminated. So we're going to talk about some of those things and kind of connect it back to some recent events. And so here we are 1 year later after Hurricane Maria in Puerto Rico, and one of the big difficulties in recovering and continues to be a difficulty in recovering from that storm is the lack of access to clean drinking water. And so this is some Puerto Rican citizens filling up their carboys and bottles and things with water from a natural spring that fortunately was there, but of course we have to be careful of the fact that sometimes if it's not treated, we don't always have the resources in place to ensure that even this water, even if it looks clean, is clean. And then I just wanted to show you this really in the context now where we're all focused on Florence, and we kind of in our minds we think that Florence has already happened and it's over with and we were lucky and that's it. But this is a process that's continuing to play out along our coast. And later today or this week, even up in Conway, the Waccamaw River is projected to crest. And so that has some big implications. So people that were negatively impacted a couple years ago from Hurricane Matthew are now feeling the effects of Florence many days after the landfall. So it's certainly something that we need to be mindful of. And so what you see is a satellite image from NASA of the North Carolina coast. So this is Cape Lookout here, just if you're familiar with that. So this would be just north of Wilmington. And what you see is all of this dirt and all of this stuff is being washed out by all those floodwaters out into the ocean. And so it's not so much necessarily that this dark color indicates that that this is pollution, but this is probably largely decaying plant materials and things like that. But you have to assume that it's bringing everything else with it. And one of North Carolina's big industries is pork production. And so they say, I think a hog generates about 10 pounds of waste a day. And there are millions of hogs in North Carolina. There's almost as many hogs as people, and so there's a tremendous amount of waste that gets generated from the pork industry, and oftentimes there's not a whole lot of action as far as treating that and getting rid of it. Oftentimes it's just sitting in big lagoons, and whenever these big flooding events happen, there's very little that's keeping that material contained and away from our drinking water supplies. So it's something that we really do need to be concerned about. So whenever I talk about the detrimental effects of things like swine manure getting into your drinking water supply, that's really focused primarily on a biological contamination. So things like viruses or bacteria that could infect people. And so if you think about all the first responders and all the people that are out there trying to help, if they get one little nick or cut and they're in this water, it could be a very, very bad medical situation because of that biological contamination, even if they're not actually ingesting the water. So we tend to have more acute health effects, so more immediate health effects from this type of biological contamination in general. But the health impacts of chemical contamination sometimes can be a little bit harder to recognize. because oftentimes it's the chronic exposure to these contaminants and these pollutants over time that can negatively impact your health. And then depending on your genetic predisposition, you may develop cancer that ultimately was caused by something in your drinking water, but your neighbor may not. So it's a very difficult problem to unravel. And so what we're going to do is we are going to be talking quite a bit about the heavy metals that are major contaminants, and then also some what we would as chemists call organic contaminants. And so I recognize outside the field of chemistry that the word organic is can be used in a way that's sort of favorable, right? To organic milk or organic whatever, but to us, all that means is that it's a carbon-based molecule, carbon-based type compounds, many of which are toxic and detrimental to our health and the health of our ecosystem. So we will be going over a few of those. There's far too many to cover them all in a single class period, but I wanted to go over some things that you may have heard about in the news or things that maybe have some local relevance to us. And so the big one that comes up with heavy metals is the contamination of water with lead. And one thing that I always like to interject into my lectures, whether it's general chemistry or some of my more upper level advanced classes, is just to tell the stories of some successes that we've had, because a lot of times whenever we talk about this environmental stuff, it's all gloom and doom. And you think that we're just unable to, these problems are just not surmountable. But that's not true. Just as an example, in lead used to be a major source of lead in the environment, used to be the leaded gasoline. So whenever you go and fill up your gas tank now, you notice it says unleaded, and your whole life it's been unleaded. But really in the, they started to phase out lead in gasoline, and so you can see that we had this precipitous drop in lead in air from the combustion of fossil fuels, and that could have ultimately gotten into water supplies. And so this is a huge success, and I wish that we celebrated these successes more and talked about them more, because it just goes to show how you can reverse. These are solvable problems. Everything that I'm talking to you about today is a solvable problem. And so I hope that you at least take some good environmental aspects away from this. But of course, we certainly have to we also have to recognize whenever we're not doing so well. And so I'm sure that you all have probably talked about the contamination of water in Flint, maybe, or maybe heard about it in the news over the last several years. So that was 4 or 5 years ago, I think, that the Flint lead crisis started. There's still people today in America that do not have access to clean water in their homes. And I think that that's shameful, and I hope that you do too. And one thing that kind of gets confusing, I think, for the general public whenever we talk about chemical contamination is one thing that we need to realize is that the poison is in the dose. And so what that means is that it depends on how concentrated these things are. So just because a contaminant is detected doesn't necessarily mean it's a threat to your health. And so, and it can also be hard to understand some of these numbers because they're very small. And so for these very dilute concentrations, we tend to convey this in this parts per billion scale, meaning that out of a billion molecules, one of them is going to be a lead ion. And so that would be 1 part per billion. And so just down the road in Detroit, only 2 parts per billion. Well below, what we call our cause for concern by the EPA. So these are just visual representations that are meant to give you a visual to kind of compare these different concentrations. And so now if we go to Flint, typical Flint water was found to have basically 10 times that of what we saw in Detroit, and then some other analyses that were shipped off had drastically higher concentrations. And the reason for this large variation has to do with the fact that the lead is coming from pipes. And so everybody's water is taking a slightly different path to their home. And so again, neighbors can have very different water quality just because of the nature of their pipe system. And so we saw some extremely concerning numbers in Flint. And I think what's even more concerning to me is the fact that people discovered this problem in Flint because they noticed their water tasted weird. They noticed their water looked murky. And so eventually they sought out more information. Actually, a woman contacted someone, at Virginia Tech who was able to run the proper analyses to confirm what was contaminating the water. So I'll have to not talk so much on each side. There we go. So it's concerning to me because sometimes contaminated water looks clear, it tastes fine, sometimes we're not always able to sense these things. It had to be very severely contaminated for people to notice. And so I do question, whenever we're not investing in our infrastructure, whenever we're not always doing as much testing as we should on our water quality, I wouldn't be surprised if there are other places that come to the surface that are shown to have problems in this area. And so just a little bit about the chemistry and sort of why was this happening in Flint? Why wasn't this happening in Detroit? What was going on there, at least as far as the chemistry is concerned? And so what happened is, and I will talk about this a little bit later in the talk, is that they found that they had conditions that were tending to produce what are called disinfection byproducts. So one of the very first things that we do with, anytime we take water from surface water or groundwater, and then before it comes to your home, it goes through a disinfection process, as anyone would hope it would, right, to get rid of that biological contamination. But those disinfectants, those chlorine-based disinfectants, can also react with some carbon compounds that themselves are not toxic, but after a series of reactions within the water purification process, you can get these what are called halogenated compounds. These trihalomethanes, a lot of those are associated with, are suspected or known carcinogens. And again, this gets to the heart of one of the difficulties with these things is that the level, and then we don't always know exactly what the disinfection byproducts were. But they found that they were getting some disinfection byproducts that were actually regulated. There's very few that are. And so they were actually told that they needed to, whenever they found that they had this high level of trihalomethanes, they added what's called ferric chloride. That's called a coagulant. It's really meant to kind of draw out some of that brown organic material that's in the raw water before treatment so that you have a little bit less of that starting material to make these disinfection byproducts. So the reason that they did that is they had changed their water source to save money, and unfortunately the water that they used when combined with the ferric chloride was very corrosive. So if you ever do any boating or anything along the coast, you know that seawater, salty water, is very corrosive. And so that was sort of the nature of their water. And so as that water is traveling through these pipes to people's homes, just like seawater can rust a boat, you can have this corrosive drinking water corrode the pipes. And so they were not detecting the iron at the water treatment plant, but later it was only by the time it got to the tap and traveled along the way. They could have done one very simple thing to prevent this entirely. They could have added what's called a corrosion inhibitor. So this would be a phosphate compound here, this molecule here, and that would basically cause a lead phosphate layer to form on the inside of the pipe. And as long as it's not mobilized and it's not getting within the water and it's staying just stuck to the pipes, it shouldn't be a health concern. So for some reason they failed to do that. There's a lot of questions surrounding the management of their water supply and how local leaders really maybe fell short of their responsibilities to the public. So that is sort of the chemical basis for how that has occurred. And unfortunately, you can see that the road to getting back and also earning back that public trust has been severely hurt by that. Another heavy metal that you have probably heard about is mercury. So mercury is a neurotoxin. People that are exposed to mercury or suffer from mercury poisoning tend to have decreased cognitive abilities. And so if you ever read Alice in Wonderland as a kid, the character, the Mad Hatter, that character is thought to be sort of a symbol of mercury poisoning. Hatter is, I guess, some adhesive or something that they used to use back in the day had mercury in it. And so that is how that profession got associated with some sort of strange behaviors, we'll say. And so for us, our number one potential source of mercury is eating seafood. And so, we live by the coast. Seafood can be a sustainable protein source, but unfortunately, some larger species of fish tend to be enriched in mercury. And so mercury has a very curious sort of path through the environment, but it's a good example of how all of these things are connected. We don't really associate our power supply with the quality of our food supply, but they are related. And so whenever we burn coal for electricity, and so we're all, a part of this problem, right? We all use electricity, and so some of our electricity still comes from coal combustion. And whenever that coal is burned, the mercury, the trace amounts of mercury are present in any coal, depending on where it's from, different levels. But that mercury gets suspended into the air, and then it eventually will fall out of the atmosphere either through rain or just dust settling. And a lot of that mercury will then go through some transformations in the environment that make it a methylated mercury compound, methylmercury, and that's especially dangerous and especially likely to accumulate in the tissues that are in fish, and then for us, the types of proteins and tissues that happen to be present in high concentrations in our brains, which is why it impacts your cognitive abilities in particular. And so mercury is one of these things, and there are other examples of this, other types of compounds and chemicals that do this. It is affected by bioaccumulation. So you have this magnification where these little baby krill might consume some water, whatever, that might be online pits, and then that material can leach those heavy metals into groundwater, into other water supplies. So that would be sort of like a slow burn of releasing these types of things. But there have been some really notable coal ash accidents in the past decade. There was a very large one in Tennessee. There's still pending litigation over that because of the cleanup effort that was involved and the sickness that people endured just from being involved in the cleanup effort. There was the contamination of the Dan River in North Carolina just a few years ago, whenever there was a breach of a coal ash pit, meaning that the walls of this pit basically collapsed and then pushed that coal ash out into the next body of water, which happened to be the Dan River. And now we're all waiting and wondering what's going to happen with Florence. So again, having this huge amount of water come in, and there's just these pits of coal ash, of toxic material, just sitting there. And once they get disturbed, then there's nothing that's preventing that from getting into water in our own community. So we're not sure what to expect. So the top picture here, this is a coal ash pit that was breached up in Wilmington. So this picture was just from last week. So you can see water spilling over sort of a barrier wall there. And then this plant in Conway, South Carolina, this is them preparing over the weekend to hopefully prevent the breaching of this plant. It's worth noting, this plant has been closed for a number of years. So just because fortunately we are getting off of coal, but the legacy of coal remains in the form of this coal ash, not to mention the CO2 in the atmosphere. So these legacies remain in our, and we need to keep an eye on it whenever we are concerned about how these different types of weather events can impact our own water quality, even many miles away from where a hurricane may have made landfall. So this is sort of an unraveling process, but I would encourage you all to keep an eye on it, because this might be close to your home and your own community. I hope that your family has fared okay through this, but I recognize that for a lot of our students that's not true. And it's something that we need to be mindful of. South Carolina has actually done a pretty good job of trying to remediate a lot of its coal pits, but they haven't been under the same pressure by the EPA as they were previously. Arsenic is another contaminant that can be present in coal ash. In this case, one of the sort of the most notable cases of widespread arsenic poisoning of a community was really unfortunate because it started out with the best intentions, is that because of the biological contamination of surface water, so surface water being things like rivers, streams, lakes, because that becomes contaminated with sewage and other waste, people can no longer use that for their drinking water. And so in an effort to give families better access to drinking clean water, UNICEF went around and dug many wells to help people access some groundwater, which traditionally is very clean. So as long as it hasn't, had things percolating down from the surface over many years, usually groundwater is a relatively reliable, clean source that can be used directly from the ground. However, the natural rock formations in this part of the world happen to naturally have arsenic present. It's not that anybody came around and polluted it, it's just that the arsenic that was present in those, in that groundwater is in a form that is not toxic, but then once it comes up to the surface and reacts with oxygen in the air that's in our water, then you can have a more toxic form of arsenic. And again, it's the chronic exposure to this contaminant that made it particularly hard to pinpoint, is that the fact that it's not that their water tasted weird, it's not that people got sick immediately and they knew right away, it's over the course of many, many years of people drinking this water that the chronic diseases that are characteristic of arsenic exposure became apparent. And so it's a really tragic story, and one that I think that they managed to shut down most of the affected wells, but it is an example of how even whenever we don't understand all the chemistry of a system, even things that are otherwise should be clean are still not suitable for our human consumption. So that kind of wraps up my heavy metals part of it. So now I'm going to move into more organic contaminants. And again, all I mean by organic is not that I mean it's natural. You'll see there's nothing natural about this stuff that we're going to talk about. A lot of organic compounds that we have in plastics, these are carbon-based materials. They are petroleum-derived materials, and they have many uses. So let's not forget that there's been a huge benefit to our ability to manipulate organic compounds into medicines that we need, polymers like plastics that improve our quality of life, pesticides, herbicides, and then I've already mentioned disinfection byproducts. And so one thing that can be complicated about understanding the way that organic contamination can affect the environment is that these compounds are labile, meaning that they're reactive. So these types of compounds, it's not just, there's the primary pollutant, there's that thing that maybe gets released from the factory where it's being produced, but then there's also what we call secondary pollutants. And so, for example, one of my colleagues in the chemistry department, she does research on the degradation products of pharmaceuticals. So a lot of pharmaceuticals, even after you take them, they come right through, or sometimes people dispose of them by dumping them down the drain, and those things can then break down into other substances that we don't really know a lot about the toxicity of. And so there's sort of a dual role that these things can play in the sense that that you have that potential pollutant from the source itself, or these potential degradation products that are not always easy to pinpoint or recognize. So, perfluorinated octanoic acid. So all that means, if you pick out that octa in there, that just means 8 carbons. And so this is the way that we would represent this molecule in chemistry, where each of these junctures is a carbon atom. And each carbon usually has 4 things around it, 4 other atoms around it typically. And so you see each carbon is attached to 2 or 3 fluorines and then another carbon, making this long chain. And so this is a material that's used to produce things like Teflon. So Teflon coated pans and things like that, great non-stick material, but unfortunately, because of the health effects that were eventually recognized with this compound, and it affected the workers in these chemical plants the most, these types of things have been phased out. So we no longer use these types of compounds and products, but one thing is that to recognize this is the same thing that makes this type of material useful to us is the same thing that potentially makes it a problem in the environment because it's so persistent. So it's not that, if it's a very stable compound, that could be good for, say, a coating on a pan that you want to use for many years, but if that same compound then gets out into the environment, then that same compound could potentially negatively impact the environment for many years to come, even after its use gets phased out. And one interesting thing about the way that chemicals are developed and regulated is that sort of our mantra in the US is that if we don't know it's toxic, then we don't regulate it. End of story. So it's not hard for chemists to come up with just little tweaks to the molecule. So all they've done here is taken this molecule, broken it in half, stuck an oxygen atom. It's not hard to do. And so what this does is this essentially makes that molecule more likely to break down. That carbon-oxygen bond is a little bit more reactive. But what we're seeing is that companies that are now replacing this compound with this one that's not regulated. So this one's regulated and this one is not. So, and now we're realizing that this is getting released directly into the Cape Fear River. So just coincidentally, I had this in here from last year because this is a big topic in Wilmington. And so there you can see that this is a community that's having a lot of water-related issues. So, it just goes to show how you can have this scientific innovation to adjust your molecules, to give it the properties that you prefer, but sometimes that is a way that you can sort of skirt the regulation. And so that is just something to keep an eye on, and just, as these new materials become developed, they're really not regulated in a meaningful way. And then finally we have disinfection byproducts. So disinfection byproducts, this is, like I mentioned in the slide from Flint, this is what they were trying to avoid, is the formation of these this type of material following water treatment. And so this NOM, this is what we call natural organic material. So this is present in any natural water source to different degrees, but natural organic material is present in most of our source water for drinking water. And probably the most common way to disinfect this is just the same way that we do with the pool, where we add some chlorine to it. And so over time, eventually we can produce these disinfection byproducts, these DBPs. And so I've represented one up here. So this would be chloroform. There's a black ball in the middle there meant to represent carbon, and then you have it surrounded by 3 chlorine atoms. And so this compound, chloroform, is a carcinogen. And again, it's not that if you drink water that has some chloroform in it, you're not going to immediately develop cancer. But if you drink it every day, it's in your coffee, it's in your food, it's in everything, it's in the produce that you bring back from the store and wash. So you have the potential to be exposed to these things. These smaller compounds are regulated now. So another success story regarding environmental chemistry is the Safe Drinking Water Act, the Clean Drinking Water Act, that has significantly improved our access as a whole to clean water. But unfortunately, because there's many possibilities for the disinfection byproducts that can form, that we're really only regulating a small portion of the potential ones that could form, and it's really hard to anticipate exactly what types of molecules may form, which ones are toxic, which ones should we be concerned about. So it's a huge uncertainty associated around disinfection byproducts in a very active area of research. So because there's limited information about not only what those possible compounds are and their associated toxicity, we really don't have we don't have much regulation regarding disinfection byproducts at this stage, because we just simply don't always know every single thing that's in your tap water, which is, I understand, is a little bit unsettling. So we obviously need to do better with regard to ensuring that our water is treated. And so I mentioned this quote before, is that one thing to kind of keep in mind is, like I say, I always hear people say things like, oh, I don't want any chemicals in my food, I don't want any chemicals in my beauty products or whatever. It doesn't, all that, everything's chemicals to me. We are chemicals to me. So whenever you hear about these things, it is good to be a little bit critical of it. You know, think a little bit critically about what people are trying to tell you. A good example is that a couple years ago, I think there was a big article, a whole bunch of newspapers picked it up about how there was this toxic compound in mac and cheese. And so all that powdered mac and cheese packets, that they found it in every single brand that they tested. Now, it was not clear to me from reading any of these news articles what that concentration was. You know, so one thing I would question is, just because it's detected doesn't mean it's poisonous. And so another thing to recognize also is people that are outside the field of chemistry. So my field is analytical chemistry, the field of making chemical measurements, and we're getting better and better and better every single day at detecting things, which is a great benefit. Just think about disinfection byproducts and understanding what types of things may form. We would be better armed to assess the potential threats. But on the same hand, these advanced analytical capabilities have made it so that it's very easy to detect very low concentrations that may not be a concern at all. Unfortunately, a lot of times we don't have a detailed toxicological studies that we need to say for certain, but just keep that in mind. So just because you're exposed to it. Another thing to keep in mind is that not just the concentration, like I showed you with the Flint water and sort of like the varying levels, but the length of exposure. And so this is another variable that's hard to really pinpoint, is not everybody is going to be exposed to that for the same period of time. If you have your mac and cheese every once in a while, probably not a big deal. But if you're eating processed foods for every single meal, every single day, then you're exposing yourself to a lot of the types of compounds that they were finding in the mac and cheese. It was really just a product of being in contact with a lot of plastic and things through the food process. So there's a lot of kind of things to keep in mind, and so I recognize that it's really hard as non-scientists to kind of take this information and understand what to do with it. But I hope that what I've presented here today has given you some insight into that. And I also hope that you recognize the places where I know a lot of you are business majors, and so you're trying to think about your career and how this all fits into your career. Just think about the lack of leadership that has to be present at a company to just leave your garbage, your coal ash in a pit and walk away. Just think about the lack of responsibility. So I just hope that as you grow into your professions and you become business leaders yourself, that you take seriously the larger responsibility for the greater good that we all have. And so whenever we are not careful with the waste that's generated from these industrial processes or power production, then we are not doing our due diligence to ensure that those costs then become externalized, right? So now if we have these coal ash breaches, then it becomes everybody's problem. And our tax dollars go to spending millions of dollars cleaning up what could have easily been prevented with better planning on behalf of the corporation. So I hope that you kind of can take some of this information and allow it to shape how you might approach problems and things in your own field. Be happy to take any questions.
Who wants to start?
Questions?
I just want to make a statement. The first thing I want everybody to realize, Flint, Michigan is one of 6,000 water systems in the United States with problems. So
Yeah.
it was, even though they focus just on Flint.
It's
a
widespread.
national, it's actually a national problem.
Mm-hmm. And one thing to also notice is that it's not a mistake that it's people in Flint, Michigan that had bad water. It's not a mistake that it is an economically disadvantaged community that suffered these consequences. It often is the case that the poor and the young have to bear the burden of these things. And so a lot of these things are problems that we know are present, and people have just decided to kick the can down the road. So I really hope that through generation, a lot of this behavior stops, because people traded profits for your better interest. You're going to have less access to clean water. You're going to have less clean air because of decisions that business leaders years ago made. And so it's just something to keep in mind as you move forward, to hopefully not continue can kind of break that destructive cycle that we have.
Some of you have some questions, hopefully, that we're going to use in the podcast. I have a question. We watched a documentary out of Germany called Plastic Planet. The gentleman that did the documentary, his great-great-grandfather invented plastic. So he was curious as to long-term outcome. He said in that documentary that you cannot, if you drink oil, a can of petroleum, just drink it, it will kill you. And then we had a second, Dr. Bauerschmidt came in, and he's talked to me about, isn't diesel supposed to be safer? And he starts screaming whenever I say that, because our buses here are diesel. And I just wondered if you could just talk about what's happening when you drink that petroleum, when you're breathing that diesel. What's the carbon doing to the body?
Yeah, I mean, I don't know about just drinking the straight crude oil, but as far as whenever you are breathing air, dirty air, you see the coming out of the bus or the truck or whatever, those, what you're seeing is particulate matter, and that is air pollution that's associated with not only lung problems, but also heart disease. So, and in particular, what is dangerous about that particulate matter is the very small material. So there's very small bits of matter that can easily get into your lungs. So large particles and things, like the little hairs and things inside your nose, should help filter that out. But the smaller it is, the deeper it can penetrate into your body. In that, a lot of the specific health mechanisms as far as how your body metabolizes that, or what specific parts it is impacting, and I think a lot of people are still trying to figure that out. Particularly the connection between air quality and heart disease is not as obvious as the connection between air quality and lung disease. So, yeah. So,
Okay,
yes,
so John, what question do you have on your list?
I just wrote down points.
Got a question?
I do not. No.
Okay. Sam?
You must have a question. Maybe you read an article or you saw a product or
Okay,
something.
Josh has a question.
What are some other successes that have?
Okay, good. So I mentioned the lead. Smog, it tends to not be a big problem in places that it used to be. That's largely because of catalytic converters in cars and having regulations regarding cars. Let's see here, what else? I mentioned that clean coal only refers to reducing sulfur emissions. So that has a big impact on acid rain. So rain is not nearly as acidic as it was even probably 20 years ago. So again, I mean, I remember whenever I was in grade school, everybody was talking about acid rain. Now nobody talks about it. And fortunately, we've largely figured that one out, and have put in place regulations that have been very effective. I'm trying to think of some other ones. I think overall, globally, more people have access to clean drinking water than ever before, even though we hear all of these doomsday stories about drinking water. And we're just concerned about the fact that we do see all of these other events happening that can impact that. And then, this is a big one, about the ozone hole. The ozone hole should repair itself in your lifetime because chlorofluorocarbons have been phased out. So that's something to celebrate. If we had not regulated chlorofluorocarbons the ozone, we'd all be walking around with SPF 80 on every day. Like, it would have been bad. So that's another big one.
Noah, you have a question?
Not right now.
Okay. Tucker?
Not really.
I'm sorry?
No, not at the moment.
Michael?
I'm saving mine for the interview.
No, you can practice on her now. Gives her a
Okay,
chance to,
yeah,
yeah, it gives her a chance to warm up.
yeah.
Well, let's see, is there like anything that they can do with coal ash, like other than just leave it lying around?
That's a good question, because it's interesting that you say that because, for example, because that's a great way to approach it, because if you can make it commercially feasible for people to just by virtue of the fact that their waste could be a useful, a useful source to make something else. So for example, the sulfur emissions that are pulled out of smokestacks with coal-fired power plants now, that is used to make gypsum, so like plaster. So that's an example of how you can take something that would otherwise be a detrimental pollutant and makes a commercially viable product. I don't know about coal ash now. I wish I could. I don't know of anything.
Also, another thing about the coal ash is if they're like, we're in a very flood prone area, right? Why don't they put like barriers or something else around to help prevent things like leakage like that?
Yeah, so now they're supposed to be lining them. That should give a better, less penetrable barrier between the coal ash and the surrounding ecosystem.
By lining, do you mean like a kind of like a flood wall or?
No, I just mean like a tarp, like a plastic tarp that would line like a big pit. And then as far as the walls are concerned, there are walls. It's just that now floods are getting to the point that they're breaching those walls. And then also because a lot of these coal ash pits are on sites that are no longer really maintained, that sometimes they can just crumble in on itself, and then those walls crumble in, and then that pushes the ash out. So even if you had a high wall, if the integrity of the walls of the pit are compromised, then that could be a problem. So and then the next question is why don't they? You'll notice that all of these coal ash pits, they exist right next to the power plant. Well, why don't they take it out somewhere else? You know. And again, it just becomes somebody else's problem. But of course, that's expensive, right, to transport it. So unfortunately, the cost of lining the pits, of maintaining the pits, of building more structurally sound pits, it's all money, you know. And so if nobody is telling corporations that they have to do that, then I don't think they will choose to do that.
And
I
just
could be wrong, but I don't think that they would choose to spend millions and millions of dollars to prevent a potential catastrophe.
And just understand, in architecture, people that are choosing to build within 7 miles of oceans are being told now that they have to raise those houses up 22 to 23 feet if they want to be safe over the next 25 years. So if you're going to be building a 25-foot wall around a coal ash pit, you're building a dam, and that, you know, there's got to be a better. Open pits are not the solution, I don't think, to this problem.
No, and I don't know what is the solution either, because whenever I look at pictures, I'm just always astounded by how big they are. You know, it's hard to comprehend.
Too much to move to like a silos.
I think again that it's cost prohibitive at this point. Yeah.
Let's check with this row. Okay, guys, start in the back. Question.
I don't know.
Okay. All right. Well, I just want to say thank you. We're going to head over, but can I have